Pluto is a distant and mysterious dwarf planet that was once a member of our solar system's planetary family. However, recent startling announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a shocking revelation. They suggest that this icy world is on a potential collision course with Neptune. But how could this happen, and what would be the consequences of such a massive event? Are we witnessing a rare astronomical phenomenon? Or is there something more to this impending cosmic collision? Join us as we explore the possibilities of a Pluto-Neptune impact. Pluto, a former planet that was demoted to a dwarf planet partly due to its peculiar orbit, remains a subject of fascination and study in the astronomical community. According to recent predictions by leading scientists, Pluto's trajectory is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the red flag of a possible hazardous collision between these two planets, which could pose a huge threat to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a staggering 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even finished one full revolution. But the intrigue doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating significantly from the near-circular orbits of the major planets. What makes Pluto's orbit even more peculiar is its inclination, angled at 17 degrees to the ecliptic plane. The path Pluto traces is much steeper compared to the other planets. This inclination and elliptical nature add layers of complexity to its orbital pattern. One of the most intriguing aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its unique trajectory. Unlike the other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its deep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amidst these complexities is proof of the intricacies of space mechanics. The three-body problem in space involves understanding how three objects, like Pluto, Neptune, and the Sun, move and affect each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. In Pluto's case, this problem shows how its path, Neptune's path, and the Sun's gravity all work together in a complex way. The terms azimuthal libration, latitude libration, and the VZK oscillation are part of this puzzle. According to astrophysicists, what's keeping all planets in their orbits is azimuthal libration. In the context of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it's positioned at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their paths from colliding. Latitude libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it's situated significantly above their orbital plane, providing an additional layer of protection from potential collisions. Another crucial component in this equation is the VZK oscillation, named after three scientists, Wiesel and Kai, who studied how things move in space. It involves the way three space objects like Pluto, Neptune, and the Sun pull on each other with their gravity. This pulling affects how they move. In Pluto's case, the VZK oscillation helps us understand why its path around the Sun is so unusual. Even though Pluto's path seems erratic, this oscillation helps keep it moving smoothly over long periods. The VZK oscillation shows that even if things in space seem wild and random, some patterns and rules keep everything in order. All of these components help keep Pluto's orbit stable, ensuring it doesn't crash into Neptune or get thrown off course. This three-body problem is important for understanding how these paths change due to the way space objects pull on each other. Studying this helps us learn more about Pluto, our solar system, and distant worlds and their stars. Numerical simulations in the late 1980s revealed that despite these stable properties, Pluto's orbit is technically chaotic, with minor deviations in initial conditions leading to significant differences over millions of years. However, these unique properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively keeping the chaos at bay. Recent computer tests have helped us understand how the big planets like Neptune, Jupiter, and Saturn affect Pluto's path around the Sun. Neptune has a special connection with Pluto, where for every 2 rounds Pluto makes around the Sun, Neptune makes 3. This connection helps keep Pluto's path steady. But Neptune isn't the only one helping. Jupiter's gravity also plays a big part in keeping Pluto's orbit safe and stable, and Saturn helps a bit too. These tests show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a stable path for a long time, even billions of years. So it's like Neptune, Jupiter, and Saturn are all working together to make sure Pluto keeps moving safely in space without running into trouble. These phenomena are essential for maintaining order and predictability in space. Without these mechanisms, the solar system as we know it would be a place of much greater chaos and unpredictability. Bodies like Pluto could potentially collide with others or be ejected from their stable paths, leading to a domino effect on other celestial bodies. For Pluto, especially with talks about it possibly crashing into Neptune in the future, understanding its orbit is crucial. This provides a clearer picture of the solar system's dynamic nature. The case of Pluto demonstrates how even the most seemingly unstable orbits can achieve a state of equilibrium through the complex interplay of gravitational forces and orbital mechanics. It also shows the importance of continuous observation and study of these phenomena to better understand our place in the universe. Exploring the depths of space often leads us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is a prime example of this unpredictability. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's path on its initial conditions, is vividly illustrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or velocity can significantly change its long-term orbit. Using computer simulations has been immensely helpful for scientists in figuring out how Pluto moves in space. These simulations use complex math to mimic how Pluto and other space objects, like Neptune, pull on each other. By changing small details in the simulations, astronomers can see how even small tweaks can make a big difference in where Pluto goes. Back in the late 1980s, these simulations showed something interesting about Pluto's path. Even though it has things like angle and latitude libration to keep it steady, its orbit can still be pretty wild and unpredictable. If you start off with just a tiny difference in where Pluto is or how fast it's moving, its path can end up looking completely different over many years. But even with all this chaos, Pluto's orbit stays stable for a super long time, like billions of years. This means that Pluto's journey around the Sun has a kind of order to it, even though it seems all over the place at first. Predicting cosmic events, especially when they involve chaotic orbits like Pluto's, is a significant challenge. The inherent unpredictability of these systems means that long-term forecasts are often fraught with uncertainties. While numerical simulations provide powerful means to understand and anticipate the future paths of celestial bodies, they also highlight the limitations of our predictive capabilities. These models rely heavily on the accuracy of initial conditions, and any slight error or oversimplification can lead to vastly different outcomes, making precise predictions a daunting task. Moreover, the chaotic nature of celestial orbits like Pluto's reminds us of the ever-evolving and dynamic nature of the universe. While we have made significant strides in understanding space, the case of Pluto reminds us how much our knowledge about the universe still remains limited. Understanding the gravitational influences of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can have far-reaching effects, influencing the stability and trajectory of other bodies within the system. So why are major astrophysicists only now raising concerns about a possible collision between Pluto and Neptune? Despite all these complex forces trying to keep such an event from happening, Neil deGrasse Tyson, a prominent astrophysicist and a pivotal figure in popularizing astronomy, provides a unique perspective on the mysteries of our solar system, particularly the intriguing case of Pluto. Tyson, known for his role in the reclassification of Pluto from a planet to a dwarf planet, offers insightful commentary on the evolving nature of celestial mechanics and the public's fascination with the unknown realms of space. Tyson's stance on Pluto's reclassification is rooted in the ever-expanding knowledge of our solar system. He views the reclassification as not a demotion, but a necessary adaptation to our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation. He sees the complexities of orbits, such as Pluto's, as a reminder of how much there is still to discover in space. The intrigue of these unknowns, according to Tyson, is what makes astronomy so captivating. Furthermore, Tyson knows how space events and discoveries shape public opinion. His statements on Pluto and Neptune reflect his understanding of the public's continuing fascination with space, as well as his belief that new knowledge brings about new mysteries. But what is his take on the potential for a collision? Tyson suggests that given the stability of Pluto's orbit over vast timescales, the chance of a catastrophic collision with Neptune is incredibly small. However, as Tyson has repeatedly emphasized, the universe is a dynamic, evolving system, and even the smallest change in conditions could, over long periods, alter the trajectory of Pluto and other objects within our solar system. Thus, while a collision may not be an immediate concern, it serves as a fascinating topic for further study and speculation. As we continue to explore the relationship between Pluto and Neptune, it's important to delve deeper into the role that the Sun and other planets play in stabilizing Pluto's orbit. The solar system operates as a dynamic system, where each planet's gravitational influence can affect the trajectories of others. For Pluto, the Sun's massive gravitational pull is the primary force that keeps it bound in orbit. However, Pluto's interactions with Neptune and the other giant planets, like Jupiter and Saturn, introduce additional complexities that maintain its unusual but stable orbit. Jupiter, the largest planet in the solar system, has a particularly strong influence on Pluto. Its gravity helps to dampen any potential orbital disruptions that might occur due to the gravitational tug of Neptune or other distant bodies. This is a crucial point because, without Jupiter's stabilizing effect, the risk of Pluto being ejected from its current orbit or sent into a more erratic path would be much higher. The way Jupiter's gravity interacts with the orbits of other distant objects, including Pluto, has been a subject of intense study for astronomers, as it provides insight into how larger bodies can influence the stability of smaller objects in the solar system. Saturn, although less influential than Jupiter, also contributes to the long-term stability of Pluto's orbit. Both Saturn and Jupiter act as cosmic guardians, ensuring that the smaller, more distant bodies in the outer reaches of the solar system, like Pluto, remain on their predictable path. The combined effects of these planetary giants prevent Pluto from experiencing drastic shifts in its orbital characteristics that could lead to a dangerous collision with Neptune. Moreover, the concept of orbital resonance plays an important role in explaining why Pluto and Neptune don't collide, despite their orbits crossing. The resonance between the two bodies is a type of gravitational dance, where Pluto's orbit is synchronized with Neptune's in a way that ensures they never occupy the same position in space at the same time. The 2:2:3 orbital resonance between Pluto and Neptune means that for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance effectively prevents the two bodies from ever getting too close, as their orbits are spaced in a way that keeps them at a safe distance. Interestingly, the resonance between Pluto and Neptune is not unique in the solar system. Many other objects in the Kuiper Belt, an area of the solar system beyond Neptune populated by small icy bodies, also display orbital resonances with Neptune. These resonances help maintain the long-term stability of the Kuiper Belt, preventing objects from drifting into orbits that could bring them into collision courses with the inner planets or the gas giants. The study of these resonances has provided astronomers with valuable insights into the gravitational interactions that shape the structure and stability of the solar system. While Pluto's orbit is generally stable due to the complex interplay of these forces, the possibility of a collision over extremely long timescales cannot be entirely ruled out. It's important to recognize that the current dynamics we observe in the solar system are the result of billions of years of gravitational interactions. Over such vast time periods, even small changes in the positions or velocities of celestial bodies can lead to unpredictable outcomes. As a result, The stability of Pluto's orbit is subject to subtle changes, and though the chances of a catastrophic event are exceedingly low, the long-term future of Pluto remains an area of active scientific investigation. Furthermore, the exploration of Pluto's orbital characteristics also raises important questions about the potential for other more distant collisions in the solar system. With the discovery of thousands of objects beyond Pluto in the Kuiper Belt and beyond, some scientists speculate that many of these icy bodies could have highly eccentric orbits that bring them into close proximity to other planets or objects over millions or billions of years. The fate of these objects, as well as the potential for collisions, is a key area of study in planetary science, especially as new telescopes and space missions allow us to observe and understand these distant bodies with greater precision. As technology advances, astronomers will continue to monitor Pluto and its orbit, looking for any signs of instability or changes that might signal a shift in its long-term trajectory. The findings from these studies will not only help us understand Pluto's future, but also provide valuable insights into the broader dynamics of our solar system, shedding light on the forces that govern the motion of objects across vast cosmic distances. Ultimately, while a Pluto-Neptune collision remains highly unlikely, the ongoing study of Pluto's orbit and the intricate relationships between celestial bodies in the outer reaches of the solar system remains a captivating frontier in astrophysics. Through these investigations, we gain a deeper understanding of the complex gravitational interactions that shape the paths of objects in space, further enriching our knowledge of the universe's ever-changing nature.